Today's topic is laboratory practicum. Since we are all sitting at home, it means you cannot do a laboratory, so we just do a virtual laboratory. So today's lesson objective is analyze the types of radioactive decay. So what's a decay? The larger the nucleus, the more unstable it. Then, when repulsive force become more than nuclear, it decomposes into smaller atoms, and this is called decay. And the radiation means the emission of energy as electromagnetic waves or as moving subatomic particles. So today's topic is radioactive decay. And from the 9th grade there are 3 types of radioactive decay. It is alpha decay, beta and gamma decay. So alpha decay means it's the emission of alpha particle. Alpha particle means it is emission of helium atom. So in the example you see the uranium atom, and it has 92 proton and 238 atoms. So when the uranium decays into alpha decay, the proton number decreases to the 2 and the atomic number decreases to the 4. The beta decay is the emission of electron. So as you see, the carbon decays in beta decays, and its proton number increases to the 1 and the neutron numbers decreases to the 1. That's why its atomic number doesn't change. Gamma decay, it's the emission of high electromagnetic energy, electromagnetic wave. So in gamma decay there is no change in proton number or atomic number. In gamma decay the high energy releases. So all radioactive radiations have the following properties. They ionize gas particles, they affect photographic films, and they produce light on striking a fluorescent screen, and they affect living things. And to say about the penetration power of these 3 decays, the alpha decay cannot pass through the paper. The beta decay can pass through the paper but cannot pass through the aluminum, and the gamma decay pass all paper, aluminum, but cannot pass through the thick lead. So let's see this decays in a virtual laboratory. As you see, this is polonium atom, and it starts to become unstable. That's why it releases alpha particle. As you see, the polonium atom changed to the lead. It has, before the decay, it has 211 atomic number. After the decay, it decreased to the 4. That's why the polonium atom changed to the lead. This is called alpha decay. Okay, let's say the beta decay. The beta decay means it's an emission of electron, and there is hydrogen. It has 3 atomic number, and as you see, the atomic number doesn't change, but its proton number increased to the 1. That's why hydrogen becomes helium. Let's take carbon atom, and it emits electron. That's why it becomes to the nitrogen atom. Okay.
As I approach with this polonium-210 alpha source, alpha travels a very short distance, maybe a couple of centimeters, an inch or two in air. So you can see I've got to get really close, within an inch, before I can even detect that alpha radiation. If I hit the reset button here, I'll show it again. I've got to get right up on that detector before it starts to see that alpha particulate radiation. To demonstrate how easy it is to stop alpha, I've got a single sheet of paper that I'll slide in between the detector and the source, and you can see it takes a minute for that to fall back down to 0, but it's very easy to block out alpha radiation. Alpha is primarily an internal hazard. If you ingest or inhale material that emits alpha radiation, it comes in close contact with your body tissue and can cause harm that way. Outside the body, it's pretty harmless. It can't even penetrate the dead layer of skin cells on our body. To demonstrate beta radiation, I've got a beta source here, and you can see already several inches away it's giving me a reading, so I'm going to range up to the ×1 scale here and hit the reset button. But obviously the betas will travel farther than the alpha. I'm going to set that there. I'm going to grab my piece of paper and stick in here, and you can see that the paper doesn't do anything really to block that beta radiation. But something like a sheet of plexiglass, if I stick that in between there, that'll block it down and send it right back down to essentially background. So it's pretty easy to stop beta radiation. It'll travel maybe 10 to 20 feet in air depending on the energy of the beta radiation or the source that you've got. The last type of radiation I want to show is gamma radiation. I've got a cobalt 60 button source here, and it's not a real strong source, so I can't show you the distance that gamma is capable of traveling. If you have a strong source, these guys could travel hundreds of feet in air. But you can see here that what I can show you is the penetrating ability of this type of radiation. I can take again that piece of paper and stick in there, and it's not going to do anything at all. If I take the plexiglass and put in there, again, that blocked the beta radiation, that doesn't do anything. It really doesn't block it out at all. What we need to shield out the gamma radiation is dense material like lead, concrete, steel, things like that. If I put the lead, I've got some lead here that's wrapped in tape. I'll take a couple sheets of that and slide in there. Then I can range it back down to that ×0.1 scale. And you can see that was pretty effective in blocking out that gamma radiation. But gamma is very penetrating. I can put my hand here and it'll penetrate right through my hand. In fact, it will penetrate through the metal back of the detector. So gamma is the one that's most penetrating. We typically use time, distance, and shielding, minimizing your time and maximizing your distance, and use shielding whenever possible to shield that. Okay.